Hello, everyone. My name is Tibor Herman, and I come from TU Budapest. But today, I would like to talk about more about the spin-off company that we are about to start up called Labi Space. And that's what you can see here. So for those of you who might not know me, let me show you our flight heritage quickly. We have flown five PocketQubes. One of them is not here, but I will talk about it in my presentation. So we are known for our Masat-1, which was still a CubeSat satellite, but we are most well known about 𝗖𝗁 and 𝗖𝗁. These were 1P PocketQubes measuring human-caused electromagnetic pollution in space. Our previous mission was MRC-100, 3P PocketQube, and right now, and today, I will talk about HUNITY and the mission results and the operation in the first few months. So HUNITY is a 3P PocketQube with deployables. The mission's main goal was a platform test for our subsystems, core subsystems that we would like to include in our Labi Sat satellite platform. And also the one payload is the 𝗖𝗁 1P PocketQube. Last year they did a talk about their experiment, and most importantly, we offered a ride for high school student experiments, which can be found on this deployable experiment panel. In the last minute, literally, like I think 3 months before integration, we contacted the SpaceX guys. They are called Tiny Tap Out, and they offer rideshare, well, kind of rideshare for ASIC development. And they also came with us to space. Oh, the other way around. Okay, so integration went really smoothly. As always, thanks for the Alba guys for being so flexible and helping with us. We integrated the satellite last summer in July, and the fit check was also successful, but that was, I think, last PocketQube conference, and this time we integrated our entire satellite with all the deployables on the sides, on the top, flawlessly. Okay, this way. So getting in contact with our satellite, it's always a challenge and very exciting times. The first few weeks, we already heard about it from previous presenters. It really is a difficult period, especially when you expect your satellite to start transmissions a few hours after launch. This was the case for us. Unfortunately, not the demo effect, but the failover mechanism had to kick in on day one because we couldn't make contact with our satellite. It wasn't because of the TLE itself. Something bad happened on board, but fortunately, our redundancy and reliability testing kicked in, and after 24 hours, the satellite communication subsystem switched over to the redundant part, and we started transmissions from the satellite, and we made contact 24 hours after launch. Since then, we've had flawless connection, stable throughout. Here you can see the initial communication between the ground station and the satellite. So we have fixed frequency, Doppler shifted, Doppler compensated frequencies, and packets from the satellite side, and the uplink commands from our ground station. So we tested everything. We checked if any of the subsystems, every subsystems work or not. This is the telemetry data from the power control unit, showing that we have good connection with the high school experiments, and also we see that all the basic subsystems are turned on, and they operate nominally. So we were discussing about initial tracking of the satellite. If you haven't flown a PocketQube or any small satellite, and you will, in the future, you will see that it's really difficult to track such a small device, because after a transporter launch, SpaceTrack and Celestrak will publish the TLEs from the transporter missions, but it's not just a few TLEs, it's a bunch of TLEs. They will provide you with an initial preliminary TLE, but that doesn't mean necessarily that that will be the correct one, especially a few days after the launch. So what we did here was gather GNSS data from the satellite and track it on Google Earth, and compare it to the TLEs, to the different TLEs. And of course, from this graph, there are several others, because we selected a few possible candidates for our satellite. We compared all of them to the GNSS data and found out that the object E was ours in the list of these orbits. So throughout the weeks, we gathered a lot of data, a lot of telemetry data. We collected, I think, more than almost 2 million packets from the satellite since November. And just to name a few, temperature is a quite interesting topic. So here you can see we have many temperature sensors on board, inside and out. So the ones that are inside, they show not too high variation, like 20-25 degrees of variation during the orbit. But those that are on the outside, they fluctuate quite violently. And even so, on the negative side, we sometimes see that the temperature sensor will find its limitations and cannot go further down than -45 degrees. We estimate this about 50-55 degrees negative from the telemetry data. This is the first time that we've tried out our own and in-house developed magnetic reluctance motors on board. These are tiny motors without permanent magnets, with its advantages, and you don't need to fly a permanent magnet which would align itself to the external field. So we tried to actuate them, and here we can see the effect on the gyro sensors readouts, that we turn them on for 9 seconds each time, and we can modify the attitude of the satellite effectively. We have to do this a few times a week, 1 or 2 times a week, because after detumbling, the satellite can orient itself in such a way that the antenna radiation pattern will have its null towards the ground station, so we have to rotate the satellite. So put a selfie camera on the satellite. Although this wasn't the intended orientation of the, well, not the orientation, the intended site of the camera. It is located here at the end of this deployable panel, but the camera angle is such that it would look at the satellite in this angle. Unfortunately, we had some hiccups. We could say the camera experiment went sideways because it didn't deploy completely in the desired angle, but we can still see the camera image from the satellite, and this way we can observe how the radiation will affect the glued parts of these harnesses. And sometimes we took some pictures with the Earth in the background, but you can only see those through the slots. We actually had loaded springs at the outside of this experimental panel, and this image gave us a clue that this shade here might be that spring which might have broken. either at the center or more likely at the solder joint. Anyways, we can take pictures like regularly with this, and it's still good for research. And we have two other cameras on this satellite, and one of them took a nice picture of our moon at full moon, so we could see the cheese in the space. So let's move on to I think the most important part of this mission, the high school experiments. We offered this opportunity for CANSAT competition teams from 2024 to develop their own experiment that we would bring with us to space, and there were 6 teams who delivered their experiments. And here are some results from these students. The 𝗖cie Sat team, they implemented different bands of light sensors. So you can see there are three different sensors in 3 different bands of light, not just visible, but I think maybe infrared and UV part of radiation, and they made some nice plots versus time in our orbit. And there's 𝗖cie. This is one of my favorites. This is a radiation measurement, background radiation measurement experiment from such a small experimental panel, and they plotted this on our globe, and they even measured the South Atlantic anomaly and the South Pole radiations from space. Let me highlight again, this is a high school experiment, and this is their result. Oh, and not to mention, they have very limited capabilities in terms of communication and data download. It's I think at least 1 or 2 orders of magnitude lower than the main payloads on the satellite. So OnionSat implemented different a resistor element which will change its resistance based on radiation. So so far they've provided a graph which shows the variation of the impedance of their element over time, and they will do further research on how what they can conclude from these measurements. As you can see, radiation measurement is really a hot topic among satellites and also students. So the SAT team, they implemented also light measurement versus time. So they plotted their temperature and also light intensity versus the time in orbit. And the last team that provided telemetry results was Seraph, who wanted to compare 2 different kinds of temperature sensors. One of them was covered by a black gunk, let's say, a black material, and the other one was glued with a transparent material, and they concluded these graphs. So temperature, light intensity, and the difference between the black and the white temperature sensors. So yeah, from here I would like to congratulate to all of these students, and I think they deserve a round of applause. And our goal is to hopefully bring more and more STEAM students or STEM students closer to space by providing them access with our satellites, which I will turn to now. So based on the experience and the subsystems that we've built with HUNITY, which was also based on the previous SMOKE satellites, we now offer a new PocketQube platform, a scalable PocketQube platform that can go all the way from, let's say, a private research mission from 2P all the way up to 6P, which is a perfect opportunity for rideshare missions. So everything is about reducing costs and sharing the costs among different stakeholders. So this photo of a 6P PocketQube frame is a perfect example for an opportunity for rideshare. We offer this through our newly founded, well, yet to be founded company, Labi Sat, and the core team behind this is the same guys as the Smoke Satellite and HUNITY. So let me tell you in detail about why and what we offer. Why do we do this and what we offer? So we want to provide a redundant, fault-tolerant, and reliable platform for either universities, high schools, or even companies that want to test their equipment technology in space. As I said, it's scalable from 2P to 6P. The core subsystems take up around 2/3 of a P, and this 2/3 of a PocketQube is a redundant platform, meaning that we have double communications, UHF communications, dual EP, well, not just dual, but yeah, at least 2-fold redundancy in the power supply rails and 6-fold redundancy in the MPPT. And we have dual redundancy regarding the batteries and sensors. We provide 3.3 volts as usual, and the batteries that we use right now are 700 milliampere hours lithium-ion batteries, 2 of them. But if the mission requires more and there's more space, so not just 2P but 3, 4, 5, 6, we can even just plug in an additional battery subsystem, and we can increase the capacity. So the onboard computer can gather the telemetry data, store it, and forward it as required. We can download the saved telemetry data in files. We can download it either through UHF, or if that's required, we can do it over S-band. One thing I will explain in more detail is the PQP, which we call this PQP a PocketQube Platform Protocol, which is based on the CubeSat space protocol, but it's not just the communication. I will talk about this soon. So our focus point at the university is radio frequency communications. We provide a very robust adaptive data rate with our UHF comms, which means that we can go down all the way down to 1.25 kilobits per second, and we can go up to 25 kilobits per second only on UHF. Right now, with the HUNITY mission, we tend to use 12.5 kilobits, and the coding rate and the waveforms are also, the waveform is GMSK as usual, but we can also switch to LoRa if that's required. In certain situations, for example, if we want just beaconing, or we don't know the location of the satellite because we have not established reliable connections with a stable TLE, we can always use LoRa, which doesn't really need a directional antenna. So, but when we establish a stable connection, we can use the adaptive data rate and go up to faster data rates. Okay, I wanted to talk about coding. So we use repeat accumulate coding scheme in the downlink, which will provide you 10 to the -5th bit error rate in just when the signal to noise ratio is only 2 decibels. So in uncoded systems, you will need much higher signal to noise ratios, 9 to 10 dBs for that bit error rate. But with this forward error correction, we can go all the way down to 1 to 2 dBs. If it is required, so the power budget needs more oomph. We can increase the capacity or the input power with deployable solar panels. We've already tested this with HUNITY, and we can even provide it in our new Labi Sat. As I've said, 6-volt redundant MPPT. The panel can be seen here. We try to stay modular, so even the payload board or the motherboard that holds the MPPTs only has to. The MPPT itself is a very tiny and miniaturized module itself, and it can be applied either on these motherboards, or we can put it elsewhere if that's required, and it can be used on its own as an independent subsystem. Also, here you can see the sensor board, which is inside this stack, and on the outside of this board you can find the 2 batteries along with the cameras on both sides. These are the 700 milliampere hour batteries that I've talked about earlier. So the onboard computer, as I said, can handle data collection. It can transmit the data packets, telemetry, and the files that are stored on board through the radio, either UHF or S-band. And it uses the PocketQube protocol. Well, not just this one, but the whole satellite bus uses the PocketQube protocol. And apart from the data storage, it can handle real-time clock and calendar, which is very useful for scheduling tasks. So if you want to do a measurement, not right now, but at a given location or time, we can schedule tasks to be done later, and it will continuously collect telemetry and store them in files, which we can download later. We could also download these files at a later time over a different ground station if that's necessary. And I would like to highlight here that our bus system, the electrical interface, is designed in such a way that these are rotationally symmetric connections. So the redundant pairs can be found on both sides of these 8-pin connectors. So altogether, this is a 16-pin connector, and we can plug it in either this way or that way. Okay, again, details on the UHF communication. This is a single chip solution with 2 redundant pairs. So this is the radio module, and we offer adaptive data rates 20 dBm at UHF, which is more than enough for a stable connection if you have a directional antenna on the ground station. It is compatible with LoRa and GMSK, and we use the forward error correction for robust links. It's fully redundant and autonomous, meaning that, as I said, day one, we had to switch over to the redundant pair, and it worked flawlessly. In terms of S-band, we also offer 30 dBm output on 2.2 gigahertz. This is not ham-band, so this needs licensing, and the data rates can range from 100 kilobits per second all the way up to 1 megabits per second. Also, on the ground station, we offer our own receiving station with rotated tracking and directional antenna. We have a 4.5 meter dish for UHF and a 3 meter dish for S-band. And this is optimized for data-heavy missions. So if you have large files that you want to store, images, high-resolution images, and stuff like that, we can use this to download that. So back again, standardized connections. It's basically a plug-and-play satellite. This is an example from HUNITY. You can see here an IR sensor measurement experiment, the ADCS magnetorquers, and the magnetic reluctance motors, and the rest of the basic subsystems. And you can see the connectors here, 16-pin 100 mil standard connectors. This was something that was important to us to have a robust connection, which is mechanically strong enough and cheap enough so that we don't have to use very specialized connectors and components, mainly because of price and sourcing as well. So the available signals are very simple: power, ground, simplex UART. So we use a single wire UART communication, not duplex, because this can be extended into a bus, so several systems can attach to it. We can also provide, we do also provide CAN interface. The data rates are 100 kilobits per second on UART and 500 kilobits per second on CAN. If there is a requirement for additional signal pins, there is space for that. So if someone approaches us and wants to do some custom stuff, we can talk about that. Okay, so let's turn to the other very important and from satellite operations standpoint of view, very important part, the PQP ecosystem. As I said, it's based on the CubeSat space protocol, but it's more than just the communications protocol. It has standardized commands for seamless operations, meaning that each subsystem can be equipped with the PocketQube protocol, and all of them will provide, for example, basic system management ports or functions like pinging it, version control, checking the Git hash of each subsystem, and the uptime of the given subsystem. If there's no direct access through the radio to the given subsystem, we can also implement routing tables. So basically, it acts as a router for the satellite communication, and because the communication is not necessarily master slave. Sorry, I was told not to call it master slave communication. It's primary and secondary communication, meaning that any subsystem can transmit their own information or packet on this bus, and we have to avoid collisions. And the PocketQube protocol is ready to do that, so we don't have too much collision, or if there's a collision, we can resend the data. So we have a very reliable in-orbit maintenance, meaning that we can update the firmware on any of the subsystems. We can monitor the CPU usage and the buffer usage of the subsystems, or not the subsystems, but the buses themselves. And we can access any of the payloads or subsystems asynchronously. So if there's a bus and you have radio communication, we could, in theory, access the satellite from two different ground stations and access the ADCS separately, the EPS separately, anything, or the payloads. We also have teletype access for testing and debugging. It's basically a terminal to your subsystem, and yeah, as I said, direct communication with any of them. So I will show you now how the firmware update looks like. So you test everything on ground on your payload. you plug it into the spare module or the working copy at the lab, and you update it over wire or over wired connection. If you're ready with that, you can do the same thing, just switch over to radio. The pipeline is the same, you just have to change the routing tables. You upload the firmware to the working copy over the air. If you validate it and confirm that it's working, you can upload the firmware and copy the firmware code to any of the subsystems on the satellite, and then that subsystem can copy on a wired connection to the target subsystem, and it can apply the new firmware on that. Here is the firmware update in action. So you can see here that most of the packets are upload packets. We do them in bursts, and we receive confirmation from the satellite that these are written properly, and we can retransmit the missing packets. So if you're interested in flying with us, we provide an example payload board, which can be accessed from GitHub. I will show you a QR code in the following slide. And we provide scalable size 2P to 5P. We support PocketQube Protocol on the RP2040 microcontroller from Raspberry, and we offer 3.3 watt power supply with standard interfaces. So our first customer is Genesis. You can find them. You heard the presentation from Photios earlier, and you can see both of our booths downstairs. So please meet us there. And for them, we designed the internal electronics for their Genesis 1P, Gen 1P capsule, and also the host satellite that will provide the communication and the orbital operation of the satellite or the capsule, and deployment of the reentry capsule. So in a nutshell, we offer a flight-proven and reusable satellite protocol, satellite platform called Labi Sat. And if you are interested in riding with us, check out this QR code or find us at the booth downstairs. So thank you very much for your attention.